Welcome back. This is Samaya Madhavan, and you're watching the series on convolutional neural networks. In this fourth part of the series, we will be continuing to talk about convolutions, and then we'll move on to talk about pooling and flattening and full connection. Hope you guys like it. You've seen how the convolution operation looks if images were represented by just one channel. So I used the blue channel from the first step to walk you through an example. Now let's look at how convolution looks when a color image is applied over three channels, right? For a 5 cross 5 image represented over three channels, the filter is now, the 3 cross 3 filter that we saw in the first step is now replicated three times. And it's done once for each channel. So the input image is a 5 cross 5 cross 3 image, and your filter is a 3 cross 3 cross 3 filter. The output, however, is still a 2D array. So in this case, it's a 4 cross 4 array. So what happens? Convolutions on the same pixel through the different channels are added and are collectively represented within each cell. So if you were to look at the first filter that's being applied over here, so like that, and then the first three over here, and then the first 3 by 3 on the red channel. So previously, after applying the 3 cross 3 filter over the 3 cross 3 cell from the blue channel, you'd get a value, and you would do that the same way for the green channel, and that would give you a value. So let's say the value over here is X and the value over here is Y, and then you do the same for the red channel and the value for that is Z, right? So now what you do is you add them. So you just add all these three values. It could be positive or a negative number. And then you collectively, write that into the output cell. So in here, you see that the output size is, generally formulated by this value over here. So yeah, so if you do the math behind this, you'd see that you'd get a 4 cross 4 matrix. So what I want you guys to observe over here is that irrespective of having three different channels, your output still is represented within the same size as the first channel. So the number of channels doesn't have the impact on the feature map that gets generated. So that was how convolutions are applied over all the three channels, being the red, green, and the blue channels. Let's now look at how convolutions are applied to more than one filter. So the first example that we saw was an edge filter, right? And we applied that over the RGB channel, and it gave us a 4 cross 4 matrix. Now, an image can have multiple features. So for example, an image of an apple can have features to capture the edges, which are probably a little on the oval end, right? And then it could have another feature wherein you want to capture the leaves, if there's a leaf present in the apple, or the stem of the apple. So each of these would be filters, right? And the more filters that you have, the more features that you're able to capture. So here you see how we've used three filters. So that's F1, that's filter 2, and then that's filter 3. And then from our previous slide, if you recall, this same filter is repeated thrice, one for the blue channel, one for the red channel, and one for the green channel. And the output is a 4 cross 4 matrix. And the same for filter 2, it's been repeated thrice for each of the channel, and the output filter map is a 4 cross 4 matrix again. And then again, I'm sorry, it should be F3 over here. And then you do the same for filter 3, it's being repeated thrice, and you derive another matrix over here. So you see that the output filter map is it has an extra dimension now, and the dimension being the number of matrix. So if you combine all of these together, include this, it's a 4 cross 4 cross 3, which is your number of filter over here. And that's how you generalize your, feature map, the size, the dimension of your feature map. So this is assuming that the stride is 1 and the size of the feature map, the feature map, I'm sorry, would actually change with the change in your filter size and the size of your input image. That said, we'll move on to the next topic, which is pooling. Pooling is the process of summarizing the features within a group of cells in the feature map. So you take the output from convolution and you apply pooling to it. So the summary of cells can be either by taking the maximum or minimum or average within a group of cells. So each of these methods is referred to as, a min pooling or max pooling or average pooling. Pooling is also referred to as downsampling because essentially you want to reduce the size of your feature map while still trying to retain the effective features that you've observed through convolution. And by applying pooling, you're able to compress the dimension of your feature map further down. So the animation over here, it shows how max pooling is applied. So for a filter of size 2, what you do is you apply 2 cross 2 matrix. So for every 2 cross 2 matrix over here, you take the maximum value between these 4 values and then you populate them here. So within the first 4 elements over here, you see that 370 is your maximum value. And then you slide it by 1. So you're assuming stride is 1 here. You apply 119 and then the same 119 over here and 251 in this case. And that's how you populate all these values in the output cell. So that's everything about pooling. So if you, go through the videos presented by Andrew Ng, he would mention in his video on pooling that there's no real proof around why pooling works. It's only based on a lot of experimentation that people have found out that pooling results in effective representation of your features in your input image. So you can imagine pooling as a way to summarize information from your neighboring cells. And at the same time, you're downsampling the size of your the feature map that you've acquired through convolutions. So that's everything about pooling. Let's move on to the final step. It's called flattening. So if you recall from the steps from CNN, so you can remember that CNN is a sequence of steps that are performed to effectively capture the important aspects of an image before applying ANN to it. In the previous steps, you saw different transitions that are applied to the original image. The final step in the process is to make the outcomes of CNN be compatible with an artificial neural network. As you would recall, an ANN would take an n cross 1 vector as an input size. So we need to just find a way to represent this matrix in the n cross 1 vector format. So note that the previous example shows. So over here, if you see that you're basically taking the outcome of the previous step, which is a combination of applying RGB filters on the RGB channel and also applying several filters, and then you've also downsampled it by applying pooling, and then you come out with flattening, which is being fed to the artificial neural network. That's everything about the individual steps that happen within the realm of CNN. I'll now pull back the original image that we showed during the beginning of CNN, and hopefully it's starting to make a lot of sense now. So what you do is, you take an input image, and this is just recollecting everything that we have gone through so far. You begin with the original input image, and it's represented using its, pixel values over the RGB channel. So that's over here. So that's image channel. And then you apply a round of convolution, which is, basically convolving your image from the RGB pixel representation by applying several filters to it. And then the dimension of this is going to be, whatever number of filters that you apply. So if you had applied three filters over here, it's going to be of, three dimensions over here. And then you run that through pooling, which is essentially downsampling. Um, so you take that, and then you could again do, any number of convolutions and pooling as you wish. And here's where you would start designing your, your specific convolution neural network by adjusting how many filters you want to use, or or how many rounds of convolutions you want to perform, and how many filters you want to apply for the second round of convolution. Do you want a third round of convolution? So these are all the variations that, as a deep learning model trainer, you would try variations around. And then these steps can repeat as many times as you would want. These are all the parameters that you'd be tuning to check to see if your model is performing better or worse. And then the final step, as we saw, was converting this to an n cross 1 vector. And then you apply that to a full connection. And a full connection, they again can be any number of full connection. Over here, we are just showing one layer of full connection. You could have several layers of full connection to make the final prediction, which would predict to say if your output is an apple or not. And this whole steps over here would happen in repeat. So your image channel conversion is going to just happen once. But after that point, you keep making changes, come back with an output, and then your gradient descent is calculated at the error step, and then you apply gradient descent to every learning parameters, and then these steps are repeated in loop until you achieve the model performance that you are aiming for. Thank you for watching this series on convolutional neural networks. Hopefully, you guys were able to understand at least parts of what I tried to explain. Keep me posted. Let me know if you guys have any feedbacks or other tutorials that you would like for me to present. Again, this is Samaya Madhavan. Thank you for taking the time to view my videos. Thanks, bye.